amino acid metabolism. So we've already got a lot of acetyl-CoA in the mitochondrion from other sources. What are we going to do to pyruvate dehydrogenase? Inhibit it, right? So it should make sense that acetyl-CoA binds to and inhibits the complex. Right? If we've got a lot of NADH in the mitochondria, where would that NADH be coming from? The answers end up being very repetitive. Where would that NADH be coming from?
Fatty acid.
Fatty acid oxidation. Either the direct oxidation and breakdown of the fatty acids, or the acetyl-CoA from fatty acids going through the citric acid cycle. Right? So NADH also is indicating we've got other sources of energy already in the mitochondrion. So what's it going to do to pyruvate dehydrogenase? Inhibit it. Right? Do all those make sense? Now let's flip to the other side of the figure. What have we got? Well, first, we've got a lot of AMP. What is AMP indicating? We need ATP. So if we have AMP, what's it going to do to pyruvate dehydrogenase? Activate it. What if we've got a lot of free coenzyme A? What's that telling the system? We don't have acetyl groups coming from other sources. What would those other sources be? Fatty acids or amino acids. So we've got a lot of free coenzyme A. That means we don't have a lot of other available carbon sources. We need to bring in carbon from carbohydrates. NAD, same thing. So NAD, coenzyme A, and AMP tend to activate. NADH, acetyl-CoA, and ATP tend to inhibit. And again, those patterns should make sense. It shouldn't be something we have to memorize. With just a little thought, we should go look at them and say, yes, that makes sense. Yeah?
Do those actually bind, or do we look at them as like more equilibrium?
They actually have binding sites. In the case of NADH, it may be, NADH and NAD structurally are so similar that they tend to compete for the same binding site. So the NADH inhibition may just be a product inhibition, competitive product inhibition of E3. Same thing with acetyl-CoA. Just lots of acetyl-CoA is going to be binding, trying to bind to E3, keeping what little CoA is there from binding. So these two are probably competitive. This one I think is probably, this one is allosteric because it's not a substrate, and it's contributing here. Question, Sarah? Okay. Kyle, we're good? That's no question or no clue? That was the no? No question? Okay. So, are we good with pyruvate dehydrogenase? I don't think you want to hear more about pyruvate dehydrogenase than that. So all of this sort of summarizes that. If you want to go through that. I think we've summarized it well enough. Okay. So now, right? Now we're here. We haven't even entered the citric acid cycle yet. We spent 40 minutes and we haven't even gotten into the cycle yet. So now we're going to enter the cycle. We've got acetyl-CoA, which is 2 carbons. And for there to be a cycle, you have to start with something. And we start with oxaloacetate. So we're going to start with oxaloacetate. So we're going to take the 2 carbons of acetyl-CoA, the 4 carbons of oxaloacetate, and make the 6 carbon citrate. Okay? So So we can do that here. Right? Here's our oxaloacetate. Right? Pardon me. Here is our acetyl-CoA. Now, oh, by the way, what have we got? With our acetyl group, we have this methyl group adjacent to a carbonyl. What's going to happen? What? No.
Anion.
Yeah, we're going to make an anion. We're going to deprotonate it. Right? We've got a carbon adjacent to a carbonyl. We can deprotonate that. So we're going to deprotonate that, which is going to make that a carbanion. Right? Which they're showing, right? Remember my annoyance? They show the more stable form all the time. But sometimes that's the less illustrative of the reaction that's going on. So this negative charge is going to be in resonance with a negative charge there. So that carbon becomes our nucleophile. The carbonyl of oxaloacetate becomes our electrophile. So we get a nucleophilic addition to that carbonyl. When that adds, it creates a hydroxyl group. And it creates now a 1, 2, 3, 4, 5, 6 carbon structure. So we nucleophilically add the 2 carbons of the acetyl group across the carbonyl double bond of oxaloacetate. Devin's thinking about it.
I'm just trying to put in my head what the purpose of that histidine is.
The
Is it
purpose,
to balance-
which histidine? This one?
No, the 274. Is it just to balance the reactive oxygen and the carbon?
Well, what is histidine 274 doing in our language of enzyme chemistry? Stabilizing an intermediate. It's hydrogen bonding with that intermediate in a way that helps stabilize that anionic intermediate. What's histidine 320 doing? It's acting as a general acid. So what's ASP 375 doing? Acting as a general base. Good. Right? Yeah. You sound like you've heard these terms before.
So even though the his 274 is also stabilizing not the intermediate, we say
Yeah, because it's
Well, hydrogen bonds here, but that hydrogen bond is helping stabilize this negative charge. So we would say that's actually interacting with the reactive intermediate, not just positioning something in someplace else. Okay? Now, we get a specific stereochemistry of this new tetrahedral carbon created here. How do we create that specific stereochemistry?
The enzyme.
The enzyme directs the attack from one specific side of the oxaloacetate. Right? So we get one specific stereochemistry of citrate that biological systems use. So now we get this, right? We've done a carbanion addition, and then the enzyme hydrolyzes the coenzyme A, essentially just breaks that, right? Essentially just breaks that high energy thioester, releasing free citrate and releasing free coenzyme A. What do we accomplish by doing that?
You're breaking a high energy bond.
We're breaking a high energy bond. So overall, we're making this
Irreversible.
irreversible and favorable. Right? So in this case, the high energy thioester bond we created, the energy of that is being used to make entry into the citric acid cycle favorable and irreversible. Right? In the past, what have we done to make reactions favorable and irreversible? What do we tend to use? ATP. So this is a different way of making this entry step favorable, and irreversible. And since now, once we get something in here, we're sort of committed to the citric acid cycle, what would we suspect about this reaction?
It's a committed step.
It's committed, and so it is also controlled, right? So we will talk about the control of this when we get ready to talk about the control of the citric acid cycle. So we finally got something into the citric acid cycle. Hopefully on Monday we can get through the reactions of the citric acid cycle. And on Wednesday I would like to then be able to mop up the control of the citric acid cycle so we can be done with it. Remembering that next Friday, what's happening next Friday?
No class.
No class, because some of us are going to Sigma Zeta. We may have to throw Sarah in the trunk and take her anyway.
We have no chemistry.
Next Friday? No chemistry seminar either next Friday.